First problem we're going to look at are problems I call position vector problems. So here's our position vector. So first let's do this part by part. Let's find the velocity, speed, and acceleration. So the velocity vector is just the derivative of the tangent vector by prime of t. So we have 6t. This becomes a 2 pi cosine of 2 pi t. And the last one is minus 2 pi sine of 2 pi t. Okay, so that's the velocity vector. The speed is just the magnitude of the velocity vector. So this is the square root 36t squared plus 2 pi cosine 2 pi t all squared plus minus 2 pi sine of 2 pi t squared. And this is all under the square root. So we see we have 36t squared. And here we see we have sine 2 pi t squared times cosine 2 pi t squared, and they're both multiplied by 2 pi squared. So we just end up getting here is plus 2 pi squared. Okay, so that's our speed. Next, we want to find our acceleration. So the acceleration vector, again, is just the derivative of the velocity vector. So to remember what the velocity vector is, so we're going to get 6 here, minus 2 pi squared, and that was a cosine, it's going to become a sine, sine of 2 pi t, and this last one we're going to get another, we're going to get minus 2 pi squared cosine 2 pi t. So you can also note that this is equal to r double prime t, which we'll use in a minute. Okay, so we have part A done. Let's look at part B. Find the normal plane to the curve at t equals 0 and give the definition of the osculating plane at t equals 0. So, recall normal plane has tangent vector given by t, right? So we're going to set t of 0. So what is the definition for t of 0? T of 0 is just r prime of 0 divided by the magnitude of r prime of 0. So what was r prime of 0? Well, we have this here, so we can go ahead and plug in 0. So we have 0 as the first component. Our second component is just going to be 2 pi. And then the last component is going to be 0 because sine of 0 is equal to 0. And on the bottom we have the magnitude of this thing. So this is the magnitude of 0, 2 pi, 0, which of course is just going to be 0, 2 pi, 0 divided by 2 pi, or 0, 1, 0, or j hat, right? So we have the normal vector. We also need a vector in the plane, or sorry, a point in the plane. So we know that r of 0, which is equal to, it's going to be 1, 0, 1. 0, 1 is a point in the plane. So our definition for the plane is going to be x minus 1 times y minus 0 times z minus 1 dotted with our normal vector, which is 0, 1, 0 is equal to 0. Or you can just write this as y is equal to 0. That's the normal plane. Okay. Now it wants us to write down the definition for the osculating plane. So osculating plane has tangent vector b at 0. That's the definition for the osculating plane at 0. And then we're going to want to write down the definition for b. So b of t is equal to t prime of t divided by the magnitude of t prime of t. Oops, sorry. That's actually n of t. So once we define b prime of t, or n of t, then we can find b. B is just the tangent vector. We could actually do, we don't need b of t, we just need b of 0 is equal to t of 0 cross n of 0. So this is our tangent vector. And r of 0 is in the plane. Okay, so if you have to find the osculating plane, these are the steps you need to do. You need to first find n. From n, you can just find b at the point you need it to. Just plug in t equals 0, and then find b of 0. Be sure to not plug in t equals 0 into this first, because if you did that, then this derivative would be 0. So watch out. If you get n of t is equal to 0, you probably did it wrong. Okay. Part C. Find the curvature at t equals 0. So for this, we're just going to write down the definition of curvature. Curvature at t equals 0. Well, the definition of curvature is just t, capital T, over the magnitude of r double prime. Well, we know what we just found t of t, or t of 0. T of 0 is just 0, 1, 0, so its magnitude is just 1. And then the magnitude of r double prime is 0. Let's go ahead and look at, if we remember, this is r double prime. So the magnitude of that is going to be the magnitude, whoops, I want my black pen here. We have 6. We have 0, because the sign is 0, and then we have minus 4 pi squared. So otherwise known, this is 1 over the square root of 36 plus 16 pi to the 4th. So that is the curvature at t equals 0. The last part of the problem, it asks us for the tangential component of the acceleration. Now that's again just a derivative. Remember, we can write a as a of t tangential component plus a of n normal component, where a of t at t equals 0 is t at 0 dotted with r double prime at 0. So, in this case it's 0, 1, 0 dotted with r double prime is 6, 0 minus 4 pi squared. Well, if you see, this is just this plus this, which is 0, plus this is 0, and this 0, so this thing's equal to 0. So the tangential component of the velocity is equal to 0 for the acceleration. So what would that look like in a picture? If this is t equals 0, we have some velocity vector, some acceleration vector. It's actually a at 0. And if we decompose this vector, we say this is a tangential, this is a normal, and what we see here is that there's no tangential component, so this thing is entirely, it's entirely curving in. So this is an idea of what the picture would look like.